We're ready? Great, great. Well, again, welcome everyone. I'm John Mikulski, and on behalf of the MIT Club of Northern California, I'm very pleased to see you all here this evening, and I think you'll find it an interesting presentation. It turns out what actually this presentation is part of a lecture series that the club has been putting on for about a year now that we call the Information Technology Information Society Lecture Series. And what we're actually, there's a brochure out there if you're interested in it, and what we're really trying to do is track information technology really from the chip level to the hardware and devices that those chips enable, then the software that's hosted on that hardware, and then the extra part is really the societal impact of that technology, which has of course been quite massive. Last year we were able to have programs on advanced memory chip technology, crowdsourcing, social networking. We had a couple of professors out from MIT who are the authors of Race Against the Time, a book you may have, Race Against the Machine, excuse me, a book that you may have heard, or you may have seen them on 60 Minutes back in January. So we will continue to have more programs in this area, and do pick up a brochure. Next, I'd love to thank Barracuda for hosting this. BJ, thank you so much. Did a little quick research. I'm sure I think we have a lot of Barracuda employees in the audience, and welcome to you. I think the rest of us have probably all used Barracuda products. I know the company that I ran for a while, there was lots of nice blue boxes with blinking lights on them that worked very well. So they're a very premier player in really the security space, and if you look around the room, you can see some of the products they have. And 150,000 organizations around the world, been in business about 10 years, I guess. 1,200 employees. Did I? About that? Okay, so I got it right. So I know many of us have used their products, and great products and great support, any of you that have worked with them. So tonight is about servers. We all use information devices of all sorts, whether it be cell phones, iPads, computers, your TiVo box, whatever. And really it raised the question of, what's at the other end of that wire? Some of us are, of course, very intimate with that, but a lot of us aren't. And so we started thinking about that. And what actually kind of informed our discussion was a diagram that magically has disappeared. Most of the world works in 2 dimensions. Since this is a two-dimensional graph, since this is an MIT crowd, I figured, well, we had to up the ante and have a 3-dimensional graph. So we looked at what we've come to refer to as the 3 S's of server systems. First, scale, which really impacts an awful lot of how you might put these things together. Is it a small memory server like I have under my desk at home that serves 2 or 3 people, or is it a huge server center serving a billion people like Google or YouTube? Then, of course, within a server setup, you have all the various systems, the processors themselves, the memory systems, backup systems, what have you. And then, of course, as these server systems have become so large and so important, is really the whole issue of support and how you keep them fed with power and cool air and healthy. And so we've tried to pull together a presentation that takes a look at all of those different things. Before we get started, though, I thought it was important that we always remember that with all the marvelous technology that we do develop here in Silicon Valley, we do stand on the shoulders of giants. And it turns out that in March 7th of 1876, Alexander Graham Bell received the patent for the telephone. So, meaningful day. So, with that, I'm going to turn the program over to David Walrod, who comes from the world of venture capital. He has a bio that I think all of us would envy. He's worked at Vodafone Ventures, Oak, Bridgescale. Prior to that, McKinsey Consulting. He has the what I call the triple crown of educational credentials, Berkeley, MIT, and Harvard, and has traveled and worked the world. So with that, I'll turn it over to David, and hope you enjoy the evening.
Great. Well, thank you for an intro like that. I don't know if I can live up to it. In fact, I know I can't. But fortunately, we have a bunch of guests here who really can. And yeah, I think all of us, at least I'm more of a user and an investor now, not a technologist. But we look at the cloud is a great thing. I push all my problems off to other people. I just log on and man, everything works. Not having to run an email server is so nice. I let those other jokers do it. Well, here are the jokers, right? These are the guys who actually make it work. And I'm sure all of you know real well, there's a lot of hard work behind that magic curtain or that Ethernet plug. And I think we're going to look at a bunch of different ways of trying to solve that problem. I've done some moderating before, but probably never with a panel as diverse as this group of people. And I did go to MIT, but I also went to Harvard. And so 3 dimensions are way too much for us. We're more of a 2-dimensional group at Harvard. And that's the law school, by the way. And what I've thought is instead of thinking of it as 3 dimensions, let's think of it in 2, kind of on the basic telecom stack, going from physical layer on up to more logical layers. And kind of along those lines, I'd like to just introduce the group that we have. We've got Jim Miller from Google, who runs worldwide operations, which is intimidating, I must say, and really does get that physical layer working. We've got Herb Zine from Liquid Cool Solutions, which hopefully keeps all those physical layers from melting and has a really innovative technology on dealing with the heating issue that I think we're all very aware of. I've got Kevin Brown from Coraid, who starts moving up the stack a little bit and starts storing bits for us and make sure they're available when we need them. And then Lindsay Snyder from Barracuda starts, I guess, keeps bad guys from getting in. And last but not least, Benson Young, who tracks down the bad guys and also just stops them and deters them. So I think we've got kind of going from layer 1 all the way up to layer 7. Well, not quite layer 7, but all the way up, pretty far up the stack here. So it's a great group. And what I'd like to do is kind of get going. We'll have presentations. Hopefully we can keep those down to about 10 minutes each. And that will allow us plenty of time for some questions among the group, and then most importantly, questions from the audience. So maybe we could just go in the order of the stack. And Jim, that would put you up first.
I think my freezer's coming up. All right. Thank you. Let's see if I can hold a mic and move slides forward. I think that's it, right? Will that do it? Maybe, maybe not. I think that's... that's the one. Thank you. So I've been at Google for a couple of years. I've got 3 years going on now, and I've got 2 responsibilities. I run worldwide ops, which basically builds and manages our cloud infrastructure that most of, or hopefully all of you consume. And I also run Google Energy. With the demise of Enron, we're the only private company in the world that's got a FERC license to buy and sell energy. And we run Google Carbon Neutral, and we use Google Energy as one of our vehicles to do that. It allows us to do some interesting things in the renewable and alternative energy world. And it allows us to buy and sell energy as a peer to people like PG&E and Southern Cal Edison. So with that, what's that? Pointed at the plant, sorry. Oh, the plant. I didn't hit anything yet, so it should work. Okay. So what's at the other end? Well, if you're Google, many more megawatts, many more servers, and lots of storage and tons of innovation. Because, quite frankly, we really look at the cloud as just starting. And it's funny. When I started at Google, I met our CFO the first week, and he handed me the largest check that I'd ever seen in the world to go spend. Our group spends, not inclusive of headcount, about 3/4 of Google's capital every year. And the mantra was, or the edict was, to go double Google, the size of the server network and the server farm. And We doubled that in 2010 to launch Instant Search, which hopefully most of you guys recognize as the self-populating search algorithm. But we doubled Google in 2011. We doubled Google again in 2012, and it seems to be on that route fairly consistently. So you guys all know our mission is to organize all the world's information, but the reality is that's leading to some very interesting places. So you can see Sergey. Sergey's making the rounds right now, like getting caught on the New York subway with Google Glass. We're starting to see these things proliferate all over Google. We're internally dog fooding them. I wouldn't be surprised if you don't see some of those in Palo Alto or somewhere around Mountain View. And then we've been huge benefactors to things like mobility, and obviously you guys know that we bought Motorola last year. But really, where we see an explosion right now in data is mobile, and also things like autonomous driving vehicles. If you talk to anybody inside of Google or ask Larry Page what Google's all about, he'll tell you it's all about artificial intelligence. And we just went through a fairly large strategic offsite a few weeks ago, and we looked at the future of the company and where we're going, and it is all about AI and some pretty cool things on the horizon. And by the way, probably my best moment was having lunch with Ray Kurzweil, also an MIT guy. But Ray is a phenomenal guy, and he's actually running a lab now that's doing natural language synthesis and simulation. So just Google in a nutshell, and what's the cloud infrastructure? It's massive scale. So we run the world's largest computer on the planet. I gave an all hands to Google, I don't know, 2.5 years ago, and I won't give you the X's, but I started the talk by basically saying we build an eBay every X number of weeks, and we build a Facebook every X number of weeks, and we still are on that clip today. Unfortunately, I can't fill in the blanks of the X's, but we are, by all counts, the world's largest computer on the planet. We also run, and this is something that probably a lot of people aren't aware of, we run one of the world's largest private telecommunications network. So every day, about 8 to 12+ % of the world's internet traffic goes over the Google network. And we also run one of the world's largest content delivery networks, our Edge network, supporting YouTube. So most of the videos that you see probably are not hosted in a Google data center. They're actually hosted at the Edge in one of our partner telecoms POPs. And then, just not inclusive of Motorola, not inclusive of other activities, we would be one of the world's largest hardware manufacturers. So when Gartner comes out with the traditional where does IBM and where does HP and others fit on that server list, we always kind of joke and stick our name in there and present that in an all-hands slide, because that's obviously never communicated publicly outside of Google. So the whole supply chain to build these things is pretty massive, because it's actually years long. And it really is an interesting problem to solve from a forecasting, because we have to go out and buy land and power. If you think about being tied to a public utility for something like a power drop, it takes years to get that done. And so we're at the mercy of a lot of interesting things like construction companies. And if people think about building the cloud, I have to admit, naively, when I went to Google, I thought we're building servers. Well, we've got a whole bunch of different supply chains that we run. We run we run a construction company, we run a land and power portfolio company, and then we run a whole bunch of integrated activities and projects to bring all these clusters up that ultimately culminate in serving our customers. And then I also run a really interesting group called Operations Decision Support, ODS, and I've got a bunch of Stanford, MIT, and Harvard PhDs in operations research, and econometrics, and stats. And essentially what we do is we model the entire Google fleet, and we run all the decision support around how to morph and change that. So the way to think about a Google data center is it's a few football fields in size. You'll see one here in a second. And essentially, once we deploy and populate the entire server, actually before we're done complete populating the entire server farm or building, we're actually starting to retrofit that whole thing. So all the time there's waves of continuous activity that goes not only on repair, but also on just the the actual retrofitting and upgrading and adding server disks and memory and things like that. This is a Google data center, a few of them. That's the one up in the Dalles. We've gotten much more public. We used to joke that 2 years ago, the first cardinal rule of giving presentations on Google data centers is don't. But we've been a little bit more public in the past few year or so. That's also the Dalles at night or twilight, and this is our Finnish data center in Hamina, Finland. It's the only seawater cooled data center in the world, and all these are running on an average power utilization or unit efficiency or usage efficiency of about 1.10 on average. They kind of fluctuate a little bit around that, but they're some of the world's most efficient data centers as well. And actually, interestingly enough, this is a paper plant that we actually recycle for our data center up in the Arctic Circle. No pun intended. This is what a data center looks like. Just kind of a microcosm of it. Just racks and racks and racks of servers. We design all of our own equipment now. Just the scale makes sense to do that. There's some other reasons why we do that as well. This is a rack. This is one of the first racks that ever went out, signed by that was the entire ops team at the time. Now it's a few thousand. And that's what the data centers look like today. That's the rack infrastructure, the power, the cooling infrastructure. And I have no idea why there is a stormtrooper in our data center. But I got this off the web, and I know it's ours. So just really quickly, these are the drivers that that drive how we think about it. So we've got to be very, very flexible. Speed. So we move very, very quickly, and we're lucky in that things like cosmetic standards and getting the Barracuda blue, that would never enter into our design philosophy because nobody's ever going to see our servers. So we move very, very fast, though. I talked about the breadth of our supply chains. I won't go into that. We love Moore's Law because Moore's Law, Kreider's Law, it allows us to basically double the capacity of Google by just waiting for technology innovation, if nothing else. And that's something that we're keenly aware of and watch very quickly. We take bold bets. So OpenFlow came out about 2006, 2005 out of Stanford. I think a lot of people were looking at it. I was at Cisco at the time. It scared the bejesus out of us because we realized that it could potentially erode our margins. Google embraced it wholeheartedly, and we announced just last year that we actually run our entire backbone or wide area network on OpenFlow. And we do it at, I think we're the world's only WAN running 100 gig OpenFlow networks. We do everything by total cost of ownership. I alluded to that in that whole modeling. So every decision we make is driven by TCO, and we look at, it dictates everything that we do at Google. When to transition a server, when to retire one, when to upgrade one, yada, yada, yada. And also when to, in fact, launch a new data center design. And then, we live under the uncertainties and risks of all global supply chains. We learned the hard way that almost all hard disk drive supply chains went through Thailand when there was floods last year or 2 years ago now. And fortunately, we were lucky, and sometimes it is better to be lucky than good. And then we run Google pretty much carbon neutral. We run Google carbon neutral through a portfolio of acquiring power that's green, i.e. hydro, but also putting up our own wind farms, and in some cases buying our carbon offsets and carbon credits through that. And I think that's it. So I'll pass it off to the next speaker.
Excellent. Well, thanks a lot. Herb, could you come next and tell us about how maybe Google could keep their stuff a little cooler than moving to the Arctic Circle?
So it won't be quite as impressive. Thank you, John Mikulski, for inviting me. John's a classmate of mine from Sloan School. Before I went to Sloan, I was a thermal engineer. I studied thermal engineering for 6 years. And I was the guy, when somebody would ask me if I think the glass is half full or half empty, I'd say, I think glass is too big. And so we to be honest, when I first stepped into a 21st century, state-of-the-art enterprise-class data center and looked around and felt the cold air and looked at the floor and looked at the ceiling, I said, you got to be kidding. This is a bad way to cool a hot piece of equipment in the middle of a big room. And so we formed what now is called Liquid Cooled Solutions. And the goal was to start with a clean sheet of paper. You can see how these things evolve over time so that you basically, step by step, grow the idea to the point where it becomes sort of a big Frankenstein. So we said, what happens to our team if you start with a clean sheet of paper? What would you, taking into account all the physics you know and all the economics you know, what would a data center look like? And here's what we came up with.
A new trend is emerging in the world of grid computing, and it's transforming the server industry and causing people to rethink data center design and operation. For those who've taken the plunge, the payoff is substantial. Introducing Liquid Cool, the world's first patented rack-mounted server solution, whose internal components are fully submerged in core coolant, a revolutionary liquid that is electrically non-conductive, non-volatile, biodegradable, and has significantly higher heat removal capacity than air. When it comes to efficient computing in the data center environment, the case is closed. Nothing outperforms total submersion technology. Liquid Cool systems mount directly into rack units, connecting to the core coolant exchange system via dripless, quick connect fittings. This exchange system pumps core coolant directly into each sealed chassis, fully submerging the server's internal components in dielectric liquid. The core coolant then flows out of the server chassis through the manifold system with an option for cooling inside or outside the data center. Dielectric liquid is in direct contact with all active electronics, keeping all components cool. Cool components are more reliable and last longer, even when overclocked. In traditional data centers, fans blast air to keep servers from overheating. This process requires extensive ductwork, massive supplies of power, and plenty of breathing room inside the server chassis and between server racks. As a byproduct, fans also produce their own heat and often hazardous noise levels. Liquid Cool reduces the amount of air conditioning required, allowing you to apply more of your data center square footage and ultimately your capital to compute technology, not HVAC equipment. Core coolant provides significant improvements in cooling capacity, allowing for greater component densities. This means that a Liquid Cool equipped data center will occupy 30 to 55% less floor space than an air-cooled or hybrid-cooled data center while running virtually silent. Running cooler means running longer, more reliably, and more efficiently. In fact, when compared to traditional data centers, Liquid Cool can reduce data center cooling costs by 60% or more, resulting in a substantial total cost of ownership savings. It's time to stop blowing hot air and start moving toward more efficient, more powerful computing. Start with Liquid Cool Solutions. Relentless performance through patented total liquid submersion technology.
So if we can turn on the... So... We need to kill this music. It isn't good enough. So for the data center facts. First of all, as people have alluded to, it's a huge problem. Data centers in the U.S. take 2% of all the power produced in the country, and 1.5% in the world, actually. And it's in the U.S., data centers spend $7 billion a year on electricity, and in Europe it's even, because the power rates are higher, more. A data center, you might be, Google's efficient. Their 1.1 is what their PUE is, the power usage effectiveness. Most data centers are over 2, which is a bad thing. The higher the number, the worse it is. And what we can do with this technology is reduce the total energy spend in a data center by 40%. Why? Because we eliminate the fans on board the servers, which take about, interestingly, 15 to 20% of the power of the server. 2 is we eliminate all the crack units and all the air handlers. And 3, we eliminate the chillers. You'll never need a chiller with liquid cooling solution no matter where you are in the world. There's a number of liquid cooling, irrespective of what we do. Liquid cooling is sort of getting traction. A year ago, we saw some large companies, and they weren't interested. Now suddenly they're talking to us again, and they're looking at other alternatives. There's 4 technologies besides dielectric cooling, where everything is totally submerged. And there's really 2 categories. One is refrigerant based, and the other is water based. And then those are the 2 transfer media other than the dielectrics that we use. And then inside the server, there's either the cold plate technology, which basically puts a cold plate on the processor and either water next to a processor, I don't know, or refrigerant is used to bring the heat, take the heat away. Or you have a cold wall or ceiling, where basically you circulate water or refrigerant through the wall or ceiling, and you use a fan to blow heat in to basically circulate it through the servers. In both cases, you're still using fans, and in some cases, you actually are bringing water in contact with the electronics. I find it amusing because I've been involved with data center development, and we spend so much money trying to keep water out of a data center through the fire protection system and all the money, and suddenly you're putting it actually at the servers. Pretty weird. The key differentiation, I think, here is we completely eliminate onboard and facility cooling infrastructure. We increase the server density. We basically can put 64 racks in 64 units in a 42U server rack, which reduces the number of racks by 1/3. We can massively reduce construction cost. We improve reliability because there's no threat of damage. One of the byproducts of this arrangement is that the electronics are completely isolated from air. So you don't get zinc whiskers, you don't get corrosion in certain parts of the world where air pollution is a big problem. You eliminate the risk. The other thing it does is the liquid actually dampens. It's been shown at the University of Toronto that it's not just the temperature peaks that are a problem for processors, it's the variation in temperature, and having the liquid there sort of dampens the fluctuations of temperature because there's a significant thermal inertia to the fluid. And then, of course, we cool everything. I mean, every one of these other technologies still requires fans in some capacity or other. We eliminate the fans altogether. You have a silent data center. This is the world of Steve Jobs here, so I have to refer to an elegant solution. It's simple. There's no moving parts. It's cost-effective, scalable system that uses standard size racks. Interestingly, because we eliminate the fans and some of the circuitry involved with that, it actually costs less to make a server using this technology than a normal server. Any electronics can be cooled, servers, switches, and solid-state storage devices. Components are hot swappable and easy to access. The dielectric coolant is eco-friendly and relatively inexpensive. It's a fluid that's similar to what utilities have used for decades to cool high-voltage transformers. And we've been running some of these systems for 5 years without any degradation in the fluid. There are no moving parts, and the heat exchange barriers to reduce efficiency. The pressure drop is low. We're only circulating about 0.4 of a gallon per minute inside these servers. So a rack of 64 units is about 24 gallons a minute. There's no need for mechanical refrigeration. There's no need for humidification or dehumidification. Electronics are not exposed to the tarnishing effects of air or air pollution. Noise and vibration are eliminated, and the fluid dampens temperature fluctuations. There are very few leak points, and frankly, if a leak occurs, no harm is done. Data centers are smaller and do not require raised floors or high ceilings. Water-based fire protection equipment can be used because who cares? Everything's sealed. Now, in the power room, you wouldn't want to do that, right? But in the server room. And the heat is recovered in a convenient form for reuse. So if you have like a small data center next to a athletic facility, you could use it to heat a swimming pool or the hot water. Notre Dame they don't use this technology, but they have these data centers that are next to greenhouses, and they use the waste heat to heat the greenhouses. So we license technology. I think that we made a misstep early on. We thought we were going to compete against all the big companies that make equipment like this. We've concluded that what we really want to do is license this technology to everybody who wants to use it. There's greenfield data centers where we reduce the white space up to 55% and simplify construction, eliminate chillers, and reduce energy costs by 40%. We can retrofit existing data centers that are out of power. Jim referred to the refresh rate. There's a continuous wave in these large data centers of refreshing equipment as you go, 20% per year probably. And as you refresh, we actually save energy. So what happens is you can gradually convert. And every time you refresh with this, you get more compute power for the same amount of energy you use because you've eliminated the fans associated with that batch. So retrofitting is clearly a possibility. We have a modular data center appliance, which is an interesting thing, teaming up with other companies. All we do is get a royalty for it. But basically, it's a container that's like a shipping container, and it's got 340 U in it, 200 kW, and you can put it in a cargo plane and ship it anywhere in the world. And all you have to do, it's what we call an appliance because it's completely set up. You put it on the parking lot or wherever it's going to go, in a rack or wherever it is. You plug it in, and you bring in the fiber, and you start it. And it's completely mobile. That reduces this module size by 30%. It eliminates the cooling pods. Most of these modules where people have done this is really two modules. You have to have a cooling pod connected to the IT pod. And then, of course, there's the addressable market. There's new opportunities because some problems just can't be solved any other way. I mean, there are problems in the world that only we can solve, frankly. So examples of the projects which no other technology can handle cost efficiently, air pollution in China and India. Our servers will last more than a year. Theirs don't. Because they're sealed. Low humidity, dust, and high temperatures in the Middle East. Electric car battery. We were approached by a car battery manufacturer in California. And they have a car, not a manufacturer of the batteries, but the manufacturer of the cars. Their battery packs are overheating. We can cool those by just putting an attachment to the radiator and use the dielectric fluid around the battery packs. And we can also handle special military applications. For example, in submarines, there's a silent running problem because they can't afford fans on their ships. And we're impervious to desert, sand, or salt air. And we can modify the form factor or the embodiment to really manage any kind of shape. So it's the value proposition fundamentally is huge savings in energy, a huge savings in footprint, and by isolating the electronics, we're able to do a lot of things nobody else can do. Thank you.
Great, Herb. Thanks a lot for telling us about something that's pretty interesting, a lot better than the water-powered mainframes you used to see many years ago. Kevin, could you come up and tell us about Choroid?
Sure. Hi, everyone. So I started out way back as a cloud builder. I was at a company called Inktomi. I was the first employee there, and our founder, Eric Brewer, is an MIT alum. He's now over at Google. It was a really interesting place to start my entrepreneurial career because we had to solve some big unknown problems about how do you scale this stuff out. I went over to the enterprise world. I was a VP at NetApp and did a bunch of that stuff. And now where we find ourselves is really at the intersection of those. So I'll talk a little bit about that. I ran a virtualization company we sold to Microsoft, and I came out of Microsoft after about 7 weeks, which was perfect. And and I looked at everything in the valley. I looked at about 130 companies. I was parked over at the Rosewood, having coffee with everyone, and I saw this company. I was just blown away because this really took me back to those early cloud building days of, sort of how do you build something really big? You have to build it out of small parts. And that's something that I'll talk a little bit about. And this is a lesson that is, sort of, going from the cloud and really affecting a lot of other places. So our company is really kind of a unique story. Grew up in the Linux market. Actually, can you guys hear me this way, or is it better with the mic? Mic for the recording? Okay, great. So our company started out in the Linux market back in 2004 selling storage to the Linux folks. And it was, the inventor was a guy who invented the PIX firewall, the local director, some pretty great products. And he invented a way to use raw Ethernet in a scale-out architecture to store really very massive amounts of data. Kind of a very similar model, looks kind of like what the Google and Amazon guys have done. I was on a panel yesterday with the chief strategist of Amazon, so it's kind of fun to be with the big guys. So we're sort of started out there in the Linux market, but we really kind of grew up in the last. I came about 3 years ago. We've now grown the business about 12x in 3 years. So we've got about 1,700 customers, and I'll give you a little sense of some of the kind of stuff we're doing, because it's not just the storage piece. In the old days, you used to run small data on big boxes, and today you run big data on lots and lots of small boxes, and that's a fundamentally different computer science problem. And that's really what some of the shift that's happening. And you look at the pictures of the Google data center there, just racks and racks. They don't even have chassis on them. They're just like sitting on cookie trays, right? So it's the idea of lots and lots of sort of atomic pieces, but you tie it together into a system. So one of my buddies, I'm a Berkeley guy, and one of my buddies is Tim Campos, who's the CIO over at Facebook. And we were sitting and having breakfast, and I said, look, we used to have these little boxes, and plastic, and some chips in them, and that's what you programmed. That was the computer. Today, that's an arbitrary packaging of transistors. Really, what you're programming today is the building. Then you cluster buildings or continents, right? It's the building is the computer. It's a fundamentally different way of thinking about it, but that's the unit of coordination to deliver a service to end users, and this is really kind of changing the way that computer science has to design things. So you've got some pretty interesting trends here. Data growth, some of the commodity technologies like Ethernet. So I always like to say that the fundamental economics of silicon are always about volume. So if you want to bet on something, bet on volume. Never bet against Ethernet. So that's something, and we this is very central to some of our assumptions. You look at where Google and Amazon and Facebook, et cetera, have taken IT. It's one click. It's instant. And if you go to the enterprise and say, I need some enterprise class storage, you'll spend 8 weeks waiting for someone to set it up with 5 different vendors that hook together. And you go home that night and you're ticked. And you get up on the web and you go click and it's done. And you come back in and you say, what is wrong with enterprise IT today? And that pressure, that consumerization of IT, those expectations are really going to affect corporate IT. And again, this idea of instead of big iron, we're now in an era of scale out. Moore's Law, you guys know this one, but it's having a tremendous effect on what those building blocks are. And a lot of the things that had to run at one layer of the stack now can run at one of many layers. And the cost effectiveness of that is really changing how we design it. So for those of you who have ever played with enterprise storage, here's what it looks like. It kind of sucks. So in order to get a disk in a traditional fiber channel system, you've got multipathing and Emulex and Brocade and zoning and EMC and 5 different tiers of storage and virtual instruments. You've got this tremendous complicated stack of technology just to give a disk and deliver to you. And our founder looked at that and he said, this is crazy. What if we could just give you direct attached disk but do it over Ethernet? So this is the technology piece of that I saw and I was blown away. It was brilliant to me, and it took me back to those cloud building days. And it's really that combination of what's that ethic of lots of small boxes for big data, right? And so there are a couple of fundamental technologies. One is that the storage boxes run with a distributed operating system. And that's kind of tricky to bolt on later. You have to kind of start from the beginning with something that's a distributed system. He invented a way to do very simple layer 2 Ethernet connectivity. So this is essentially a way to use raw bare metal layer 2 which, by the way, if you look today at Arista or one of those kind of networks, you can get 10 gig for about $300 a port. That rounds down to free. Right? That's a tremendous amount of networking capability that's available today. And we use it not just one pipe, which is the way that the old storage needed to run. We actually use all the pipes. So it's massively parallel and connectionless. This has a couple different aspects that are important. One is that it's very easy to morph and change and grow and be elastic because there's no connections to set up. But number two is it means that you can use it in a massively parallel way. So if you need more bandwidth, you just add more pipes. So you want to go 10 gig, 20, 30, 40, 50, 60, just plug in more, right? So this is very versatile as you look at the different workloads, the different flows in a data center. It can become very unpredictable, especially with multi-tenant cloud types. So the third piece up here we call virtual DAS. So this is really a simplifying and a virtualizing technology that makes the entire shared storage system. This could be multi-petabytes with no single point of failure, with snapshots, with flash, and all sorts of things. We make it look like your C drive. Literally, it looks like it's a local disk. And so if you look at modern applications like a Hadoop or even Microsoft's new applications, they're being designed around DAS because SAN is a pig. It's really expensive and it's hard. And you need a lot of specialists to deal with it. And so a lot of people are trying to design out that complexity and cost. And so that's a perfect fit here because we say, well, it just looks like your internal disk. But instead of going over a SCSI cable, SCSI ribbon, it's going over Ethernet. And it might be going 50 kilometers. So this is an interesting abstraction of connecting the compute to the storage layer. So one of the things that we do is we'll start out. So we have customers like Ford, Sony, GE, Home Depot, Army, Navy, Air Force, Marines, Box, Splunk, Tableau, Shutterstock, Shutterfly, AT&T. So we just in the last few years, we've gone from small Linux customers to now breaking in with this model into the biggest brands in the world. And the reason is that they just can't do it with their old IBM, EMC, et cetera, type of stuff. And so, but from a business perspective, which is important, you have to figure out, well, how do I get in? And so what we've said is we target some of the big data pain points like backup. It's not that sexy, but it's big. And in fact, it's very hard to do. To handle the kind of scale that people have with all the copies of data they're making. So we'll come and do a backup deal, but then we land and expand. And the idea is instead of having specialized storage arrays for each of the different types of workloads, so if you go call one of the big guys, here's your backup storage, here's your VMware storage, here's your database storage, here's your high-end storage. It's crazy. They'll sell you 7, 8, 9 different things that run on 2 different wires with 5 different operating systems and no common management, right? That looks like cost. That looks like complexity. It doesn't look like strategic advantage. And by the way, that's why it takes 8 weeks for you to get your application up and running. So we talked to one of the big banks. They came to one of my talks and they said, you know how many backlogged applications for storage provisioning we have at all times? 800. Think of all those money-making banking apps that are just sitting there. Someone designed a hedge trading sort of application to take advantage of an oil spike. Too bad. By the time it's deployed, the oil spike is over. Had the same discussion with the CIO of the CIA. He said, "We have more money than God. Your money." And but SAN is dead to us. Why? Because by the time we get it stood up, the war's over. Literally. So there's in the economics of this. So you've got capital expense, capex. You've got opex, and then you have something that I call velocity or time to money. And this is a really big determinant, I think, in the future of how do you design IT to make it much more agile. And this is where the end users are going to really push, just like bring your own device. They're just not going to put up with having to wait around for 8 weeks to get it. And so this has helped us really land and expand across multiple different places. Because we have very versatile building blocks that can handle SATA, SAS, SSD drives. They're all very highly connected with all the 10 gig. We can really start to soak up a lot of room. So our first deal was $250K at this retailer. The next one was $1.3 million. The next one was $3 million across 5 new apps. So that land and expand business strategy for us is starting to work. So I'm from the Plumbers Union, like some of my colleagues here. So data center has compute, network, and storage. So compute used to be big iron, like DEC, Sun, and SGI. These big servers. What happened? It decomposed into very cost-effective x86 boxes. Same thing's happening with switching. Now you get all these, top of rack, $300 a port switches. Guess who's next? Storage today is taking up 40 to 50% of the IT budgets, running big iron on custom hardware. That's I think it's inconsistent with the economics where everything's going. And flash technology in particular, what you used to have 1,000 hard drives to do, you can literally do with 2 from an IOPS perspective. So it's really changing the way that you have to throw brute force at performance problems. So if you look at what happened here, you had all these servers. What did you have to do? You had to wrap that with something to control and manage all those servers. It was called VMware and a variety of other solutions like that. Software-defined networking is coming in now to control and to get its arms around all of these networking ports. Gets what's next? Software-defined storage and making all of that programmable in one click. So in fact, we've shipped this. We demonstrated at the big VMworld conference, one click. Like Amazon, the ability to put very complex enterprise configurations on storage, but do it with a very consumerized approach. In fact, to let you program it. So the idea here isn't that you have lots of people. So you go to Google or Amazon, you click a button. You don't have gnomes running around plugging in wires and configuring things on a GUI for you. It's all software. And that's where the enterprise needs to go to get the economics and to get the way of running things. And anyone who's running and operating a cloud is doing exactly this today. We're helping commercialize that. So you look at the spectrum of here's what your father's Oldsmobile, right? Here's what a lot of enterprises have been buying, the big box kind of stuff. Here's what Google's doing on the other side. It's build your own everything down to the hardware. And we kind of sit in the middle, and we're sort of commercializing this, but bringing the economics and the programmability and sort of the scale-out architectures that look a lot more like those modern sort of big data centers. So this intersection of cloud, enterprise, it's funny, the enterprise know they need to look more like the cloud, and the cloud is starting to run a bunch of applications that turn out to need more enterprise features. We get to live right in the middle, and so we're really driving that to affect both the economics, but really to create an agility and a speed for how people use IT. That's it. Thank you.
Excellent. Well, that's phenomenal, Kevin. I'm actually in the building right next to you, and I noticed you guys got a new sign like a couple of weeks ago. What was the matter with the old one? It looked fine. I'll say that for questions later. So next, I'd like to welcome our host here, Lindsay Snyder, to tell us about, I guess, the good stuff that happens in those blue boxes that we see around the airport all the time.
Thanks for coming. It's really exciting to be invited and be part of this panel in such good company. So I'm really excited to be here. At Barracuda, I lead the cloud development. So I think the stuff that we work on is really intriguing, and I picked 2 things to talk about. I think we could expand on that and talk about more, but I picked 2 to kind of run through. I think they're kind of interesting problems that we see in the cloud. And this is kind of moving up the stack a little bit. This is more on the software layer. So I took 2 products that we have. The Barracuda Backup Server, which is an off-site backup appliance. It backs up locally and sends data off-site and stores it at an off-site location, which we then replicate to a second off-site location. So a customer ends up with 3 backups of their data, 1 local and 2 off-site. But what that means is we have a lot of storage in the cloud. And there's some interesting challenges associated with that. I'm going to go through one of them. The other is a new product that we just released, Copy.com. It's a sync agent. You should check it out. But there's some interesting security aspects associated with that I thought it might be fun. And to look at how global DDoS works and an interesting security situation that we kind of came up with there. So let's look at this. Starting with copy and dedupe, I thought I would go through the interesting problem that we ran into. And copy and many of these sync engines use a global dedupe system where they're deduping data, they're not storing it twice. And if we take a look at that, what that basically looks like, I'm just representing here a 7 meg file that you might want to sync around and have the cloud sync around for you. And the way dedupe works is the first thing, I mean, there's a couple variants of it. The first thing you do with your file is you break it up into chunks, or you break it up to pieces. And then you take each of those pieces and then fingerprint them. And I fingerprinted them with shapes. We got, square, circle, another square, star, and such, right? And we take all those shapes and we store them in dedupe storage. And one of the things you'll note there is that we caught deduplication of data between the first part and the third part, so we didn't have to store it twice. That's actually pretty common. We'll find duplicate data in like Exchange, empty space, and VMDKs. There's a lot of savings there. And anytime you're doing a sync engine or sending something off-site, reducing the amount of bandwidth you use is a pretty important thing to do. So dedupe's very important. The other big savings you have is if you throw another file in here. Notice this file is almost the exact same, but somebody must have went and changed something. Because instead of star, we have right triangle right there. See, the fourth one down. So when we go to back that up or sync it around, you'll notice that in dedupe storage, we only had to add that piece. Right? Pretty cool, pretty straightforward. There's actually kind of a problem, and I'm not going to name names, but somebody ran into a security problem with this. They had a sync service, and it worked on this very technology. The way I like to think of this, let me take a step back actually. The way I actually like to think of this is on the left you have the recipes of how you build these files, and on the right you have the storage. So when you see a new file, you write the recipe, this is what the file looks like, you put the storage in there, and then if you want to restore that 5 meg file, you grab square, circle, square, right angle, triangle, in that order, put it down, and you get your file back. Right? So this, the interesting security problem here was to do the sync, what they would do is send the recipes around. If they wanted to sync you that 5 meg file, they'd give you the recipe for the 5 meg file. And then their sync agent would go grab those pieces from the cloud, and you would now have that 5 meg file. Well, at some point, the hackers caught on to this. And I'm going to pick on Pirate Bay. And they realized, hey, we can actually make it so we're going to learn the recipes to all these movies we want to distribute, right? And we're going to make it really easy for any of you guys to search for the movies or whatever you want to pirate. You do your search, and you click, I want to watch the Superman AVI. And they'll inject that recipe into your local database, and your client will download it. So they made a search tool around these recipes because they knew that the clients would just download them, and all of a sudden, the sync program turned into, an illegal file sharing, and it was really simple to do. So now we're in this space, right? And we don't want this to happen to us. And I thought it'd be kind of an interesting challenge to kind of talk about how we solve this particular problem. Now, there's a whole array of problems, but this one's kind of fun. And the other thing to know here is this dedupe. I have 7 or 8, different shapes up here, but we dedupe, and this is probably typical of people who do global dedupe. There's hundreds of billions of these shapes up there that we match on. But one of the things that we do, the way that we prove that you didn't just click on Superman and get these recipes injected. In fact, that's really dangerous. Say you had a file that was your financial data, and somehow people didn't get access to your file, but they got access to your recipes or the fingerprints that made up that file, and they injected that into the database, and their sync client would just download all the parts to your file. Like, that's a real problem. So one of the things we got to do is when somebody says, here's the recipe to this file, this 5 meg file, we basically got to say, prove it, right? I'm not going to make you send that to me, but I want you to prove to me you have it. And the way we did that, the technique we came up with, is you take the file and is the parts that we normally break it up to. We ask for a random offsite and byte and say, hash this piece. What about this little piece down here you weren't preparing? Hash that for me. If you really have the file, this isn't hard to do, and tell me what that hashes to. And it should look like that. And if it doesn't, then I know you didn't have the file. So I thought it'd be interesting to kind of show you how that worked. The other interesting cloud thing that we do is big storage, right? We're storing a lot of data. And I like to think of a computer. When you install a computer, it can provide these 4 things. Maybe you could argue network's another one. You install a computer, it's providing you CPU, it can process stuff, right? It can transform things. RAM, or whatever, disk space and disk I/O, which I think are two different resources that a computer can provide, right? There's a difference between archiving something and then tracking changes over time. And one of the things that Moore's Law is great for, it fixes some of these. CPUs are getting faster, so every 2 years or 3 years, we have more CPU power. RAM, that's not really a big deal, at least not in the world of big storage. And neither is disk space, because those keep increasing. But the one that Moore's Law isn't helping with at the moment is disk I/O. I happen to be the guy who built the first server that's accepting traffic for the Barracuda backup system back in 2005. When I built that, it was using 200 gig hard drives. I think there was 8 of them, and with RAID, we had 1.2 terabytes. It was the biggest machine I'd ever logged into in my life. I typed DF in Linux, and it had a T for terabytes, and I was very excited. And at the time, that 200 gig hard drive, probably, I'm just doing an estimate here, gave us 75 operations per second. So our operations per terabyte, 8 years ago, was 375. And we built the technology, which was dedupe, around 375 operations per terabyte. Not so bad. Actually, we didn't even really have to think about it. It wasn't really an issue because we just did the thing and it worked, right? Very excitingly, later, 400 gig drives came out. It was like a year or 2 later. And unfortunately, they didn't give us any more IOPS. So the IOPS per terabyte went down. That was okay. 500s, you get more excited, you got more disk space, but you're starting to get squeezed on the IOPS, right? You have to start rethinking things and go back to the drawing board. The way we did it originally isn't going to work. And then terabytes came out, and back to the drawing board again, and you realize that I now have 1/5 the I/O that I did before. Now, this isn't a big deal if you want SSDs, but if you want to do big storage, this is your world, right? And then not too long ago, 2 terabytes came out. And I was like, there's half of our I/O again, right? But we got more storage. We're down to 38, or 1/10. 3 terabytes came out. They cut us down another 50%. And just 6 months ago, the enterprise 4 terabyte drives came out, where we got 1/20th of the I/O per terabyte that we did 8 years ago. And everything that you designed for 8 years ago, you kind of have to throw out the window. I mean, you got some general concepts are there, but there's a lot of things that actually have to change. And this is an interesting problem. This is somewhere where Moore's Law currently isn't helping. And I'd love for a hard drive technology to come out that is big space and fast disk. But for now, we're kind of living with these constraints. So when they're increasing when they're dropping us 50% from 2 to 3 and another 30% from 3 to 4, and we're already so constrained, we've really had to go back to the drawing board. And so far, we've managed to kind of stay up with it. And I think maybe you're planning ahead. Maybe we're at 5 or maybe we're at 8 before we break down and we're back to the drawing board again. But it's just really an interesting challenge. It's worth talking about. So this is kind of a graph I put together of what the hard drive space looks like, which are the stacks, and the amount of disk I/O per terabyte you have, which is the line graph. And it's getting pretty bad, right, depending on what you're trying to do. So on the 4, for our world at least, and I think probably a lot of people who are trying to do big data storage, it's that 4th one, it's the disk I/O that is, Moore's Law is not helping, and that's where we kind of have to be, I think, a little more innovative to make it work. So what are some techniques to lower disk I/O? Things we learned over the years. We'll probably have to come up with more, but this is what we got so far. Kind of breaking it up into the 2 different areas. There's some things you can do on the hardware side to help out with the problem. There's some things you can do on the software side to help out with the problem. On the hardware, sometimes you can realize that the SATA drives, the 7.2K RPM, the 4 terabytes that you buy, they have a lot of space. Sometimes you can separate out the long-term storage from the things that need to be really fast, like the metadata that needs the disk I/O. If you can be a little bit more intelligent and put the metadata on the SSD and the binary data or the big data on the SATA array, you can buy yourself time. And in fact, there's products out there that kind of do this automatically for you if you don't want to do it for yourself. The next one we found was instead of you have a 100 terabyte box, instead of making it one big array and then setting partitions on it for the different things you want to do, it's more efficient to make different arrays with the exact same drives rather than partitions. And the reason being is if you have 3 partitions on one array, anytime the operating system or your code is touching one of the partitions, you're swinging the heads, up and down the whole one array. You have one set of random I/O. But if you set up different arrays, they can all kind of swing independently. So just by how we format out on the RAID card the hard drives, that was pretty significant. And that's kind of the hardware side of the house. Software side of the house, sometimes you have to take different approaches of how you store the data. Anytime you can use an algorithm to determine how you store something or what something is, instead of actually tracking it, you can have some savings there. For example, when we had 20 times the disk I/O, we would actually track, the dedupe storage is on hundreds and hundreds of servers in the cloud. And we'd have a database that tracked for every piece of dedupe storage, which is 200 billion, what server it was on. It was great. You could ask for a part, and I could tell you what server it was on. We had a database for it. Well, that doesn't scale because we had hundreds of the machines that were just tracking where these parts were. So we threw out that concept and made an algorithm. The algorithm decides where the part goes. And that took out 200 billion rows of database work we had to do. Right? We replaced a bunch of disk I/O with an algorithm. So that's always an approach. Caching, of course, that's nothing new, but it's definitely very significant. Big part of making disk I/O go away. Avoid metadata tracking data. There's times where we have something on disk and we want to put it in a database or some key value store that we have this thing on disk. So now not only do you have to put it on disk, but you have to track it on disk. And sometimes you need to do that, but anytime that you can avoid doing that and just check disk to see if you have it, rather than try to track it, you can actually save the disk I/O there. And then the last thing, which we've actually find is one of the bigger wins, is try to throw out as much random I/O as possible. Because hard drives actually are very good at sequential I/O if you can get the head down and just keep writing. It's the random I/O that takes them down because of the swinging the head. So if you can rewrite or redesign what you're working on, or at least pieces of it, to switch from random I/O to sequential I/O, you get a lot more performance. And that's one of the big areas that we've now invested in, especially when we hit the 4 terabyte drives. We had to do that now that we're at 1/20th of the disk I/O that we were just 8 years ago. So I just picked those two. I thought they'd be interesting talking points. I think there's actually a lot of interesting challenges that we run into in building stuff in the cloud. One of the things that's kind of fun is that there's not a ton of people doing it. So when you're working on it, the stuff you're working on, maybe there's 500 people in the world or 1,000 people in the world and doing it on this scale. It's not big enough that when you want to look for an answer, you can just go Google it. So it helps to have communities like this where people can get together and brainstorm ideas on the challenges we're running into and how we've solved it on this side of the fence and kind of work together, come up with the problems. So those are the two pieces, the hardware thing and the copy, and that's it.
All right, Lindsay, thanks a lot for that. That was really, really good. And last, to finish up at least the presentation part of the evening, we've got Benson Young telling us about security and what he's doing to keep us all safe.
Thank you. First of all, I'd like to thank you for inviting me here. Thanks, John. I'd like to start by going over some of the issues that some of this data that we store, massive data, and how can we protect those data. And in terms of the policies and procedures, standards, and baselines, how we can tie all that together to help us protect the data. And then I'd like to go into the risk management side of it. I think protecting data is actually not a technical problem. It's a risk management problem. So we'd like to look at it from the risk management standpoint of view. And to cover the risk management, education to me is the most important. So that's human factor is often that where we do not spend enough time to consider. And I hope that at the end of the presentation, you have a couple items you can take away with. As we know, just about all corporations got hacked in the last few years. in the last several months, during the last several weeks, perhaps even while we're sitting here, someone is getting hacked. And you wonder why some of the most technologically advanced companies with seemingly unlimited budget couldn't protect themselves. And what are we worried about? We're worried about the intellectual properties, the source codes, and the trade secrets. But probably more importantly, the reputations of the company. With Google, for example, Microsoft, they have enough budgets, they have enough money, they can do any architecture, any solutions that they can do. But I think the technology is really not the solution. I think the issue is really with us, with the organization, with how we handle day-to-day operations. So I like to step back and look at any organizations. We would not run our company without HR department, without HR policies, procedures, design how to hire and operate, interview, hiring people. And we would also use the procedures to determine who to hire, so on and so forth. And there'll be standard for each positions. The requirements for each position, so we have a job description to decide who should do what. And then there's annual and semi-annual reviews to determine whether we should promote, demote, perhaps even fire someone. But in the data protection world, we don't have any of that most of the time. So to have a policy set up, we would need to consider the types of data that we're protecting, the classification of the data, as well as which data is more important. For example, we need to understand, are we protecting the integrity of the data? Are we protecting the availability of the data? For example, take NASA, for example. They can delay the shuttle launch for days, weeks, perhaps even months, if data integrity is in question. For Google, their website, uptime of the website is more important. They could serve up some data that's corrupted, but they will not take down the website. If Gmail gets hacked, they will still keep the website up and running. So as an organization, we need to understand what data we're protecting and what kinds of protection we need to build in to protect them. Procedure is the way that we implement and enforce the policy. Both procedure and policies has to be up to date, has to be a living document. Otherwise, it's useless. So take the standard. Why do we need a standard? The standard essentially defines what classification of the data should be stored. We would not store, for example, anything confidential in a cloud, perhaps not yet. And should we allow employees bring their own iPhone and store the customer list on the iPhone? Maybe not. So the organization needs to set a standard that would enforce how the policy and procedure works. It's also important to set up a baseline. We need to understand what's normal. For all the file that's on the file server, we need to know, what the checksum is, what the timestamp is, and if things get changed, we better have a way to know it. And we need to understand how to detect that on a routine, perhaps even real-time basis, in order to detect, in order to protect the data. So to set up a risk management framework, each company may be different, but the certain steps we usually would take. A couple things to think about is, what are the risks? What's the value to the company? And how much cost it's going to take us to protect it? and whether the benefit is worth the cost. So those are some of the things to consider. And it should be a living procedure. We don't just set it up once and forget about it. You always want to go back and review, make sure that we're doing a good job. Protection is important, but nothing is more important than recovery. A lot of companies doing a job to try to protect their data, but they're not ready for recovery. Once we understand the classification of the data, we need to also understand how fast can we recover them. If we cannot recover them, we're not really doing a good job protecting them. So my mantra is, you already hacked. What do you do next? And that's usually the case. Given today's data is mostly within IT infrastructures, so a lot of times when we set up risk management, IT is not really getting involved at a deep level. Those are some of the things I see in the field, and we need to get IT involved because they know where the data is. Without training, the system, it would not work. The reason is the attack are no longer only coming from outside. In fact, it never was, the biggest attack usually come from inside. And some of you may recognize the soldier on the slide. I'm not getting into the politics of it, but he leaks tens and thousands of documents to WikiLeaks website. And if there's a good baseline setup, things like that should not happen. In fact, MIT is called a hacker because they have a really good baseline setup. So when the hacking was going on, they were able to catch the person who's doing it. And without good training program, sometimes you will not detect the insider hacking, or espionage that's going on a lot of times. This is one of the slides I want to show is how we usually help our clients to protect their data. The key takeaway on this particular diagram is that the architecture here separate the users from the server applications, and from the server applications to the data. And we protect the data regardless if the traffic is coming from inside or from outside. It's a fully redundant system. The benefit is, by setting it up this way, the intrusion can be detected a lot easier. We know what traffic should be going between the application server as well as the data farm. So you can set up the intrusion prevention, only watch for the certain traffics. And anything beyond that, you know it's a hack or something suspicious going on. And the last thing I want to leave with you is do not wait, because when you're hacked, it will be all too late to do this. So start your prevention early.
Great, Benson. Thanks a lot for that. So I think now I'll throw out a couple questions to the panel. Tried to come up with some questions that I think everybody will have a perspective on, and let's see how that works. The first question I kind of throw out to everybody is, where do you see the real limits to growth? You know, right now we're kind of throwing up data centers, we're throwing up new cooling systems, or throwing up new storage ideas. Is there some place down the road where growth really starts to get tough? And kind of with my own self-interest here, where is real innovation required? Because, of course, as an investor, I'm always looking for real innovation. So the question is really two-part. You know, where does the growing get tough? And then, you know, where can you make money innovating? And I'm sure a lot of people out here might want to maybe think about that also. So why don't you just kind of go down the line with some ideas?
Sure. Well, this is where some of the designs that you see, for example, in the big data centers have said, we can't build a box that's big enough to hold the whole internet, for example. So back in the day, Alta Vista was the big search engine. It was a DEC Alpha. It's the biggest mainframe you could build. and we were coming to compete against them, and their idea was, we'll build a bigger mainframe. And so, sort of once you realize that that wasn't going to do it, that once you could parallelize and use scale, then it becomes a question of economics and operations. And you look at the economics and operations of some of the data centers, both public and private, like some of our government customers, they're immense. But you can do it, and it's really an economic, question then of it's not about can you grow, it's can you, sort of match the cost of growth to benefits and use your imagination to develop applications that can take advantage of all that power. The amount of power that's available, to compute things is shocking now. You look at how much it's been democratized. Petabytes have been democratized. Millions of IOPS have been democratized. You can fill a building up for a lot less than you used to be able to do. And so that part for me is, it's, like when the overbuilding of the internet happened, back in like 2000, 2001, they laid down tons of dark fiber, and it took about 10 years to catch up. It was Netflix across the street and some of the other folks that really started to fill that up. And so sometimes you get out of sync with the applications that can actually use it in an effective way. So for me, it's really, I was an economics major, so I look at this, and there's a lot of the economics here that you have to align the business use cases with, what's the state of the art and where's Moore's Law taking you. But for the foreseeable future, you'll be able to build bigger and bigger things. And so, the smart folks are the ones who are going to be, able to harness all of that and turn it into something that's elegant and simple and manageable.
I think the limit to growth has been really the inertia of the old systems and the legacy systems that people inherited. I think the people in this room, all of whom are basically technology people, really that's your opportunity to start with a clean sheet of paper and say, look, does it work anymore? Have we reached the limit? Have we reached the thermodynamic limit? Have we reached the power limit? C-Micro is an example of a company that looked at that and came up with a completely different architecture. We did, and we're still working on it. Google is, I think, in the way it operates its business. So the growth, you reach a point where you just saturate the existing technology and you have to do something completely different. And that's the opportunity for everybody here. Oh, you've got your own?
I got my own.
You got two.
We're scaling out.
I think we live in a bubble right now in Silicon Valley where ubiquitous broadband access is just something we take for granted. Whether it's at our home, our office, or our mobile device. And there are, vast quantities of the world where they don't have that type of access. And, if you take sub-Saharan Africa, parts of India, certainly parts of Asia. So I do believe that access, the demand right now almost seems insatiable, but obviously that can't continue forever in the developed world. So I think the developing world and the access to cheap and ubiquitous broadband is certainly a huge opportunity. The average data center today in the U.S. has a utilization of about low single digits. There are some reasons, around multiplexing and virtualization of the hardware, but at the end of the day, really enabling a much more effective utilization of existing capital is not a technology problem, but it's an economics problem and it's an incentive problem as well. And it's something that we developed some interesting solutions to that we use internally. And as we start to externalize more of our cloud, we'll start to make that more publicly available. But that's also very, very interesting. I talked to the CIO of Microsoft now about a year ago, and I was shocked by how low on average their server utilization is. But that's a lot of just idle power being consumed to basically heat a room. So that's a huge opportunity. But again, I think it's an incentive problem. It's not necessarily a technology problem.
Cool. So I agree with Jim on the bandwidth issue. We certainly see, being offsite backup and doing cloud components and sync with copy, we definitely see bandwidth kind of being a limitation amongst the customers. Not so much at the colo, there's plenty there, but definitely out to the edge. And then at the colo, I brought up the other one that's kind of going to, I think, plague us a little bit here in the future, which is the disk I/O issue as we start getting big data and need to get to it all really quickly. And I think there could be a technology breakthrough that kind of changes the market there. I actually kind of see this problem. It's changed over the years, and I expect it to continue to change. I always see it as a bottleneck problem. I have this theory that everything would happen in instant time if there wasn't for bottlenecks. So there's always something that's preventing you from going a little bit faster. And as soon as you solve one, you're now going faster. You're doing something more of something, but you hit the next one. And you just keep solving them and moving down the road until you get to where you need to be. And a lot of times where you need to be, that's only going to buy you 6 months or a year, and then you need to be a little bit farther. So the bottlenecks that we're hitting today are different than, I think, the bottlenecks we hit 2, 3, 5 years ago. And they're probably going to be different 2, 3, 5 years from now. But I think bandwidth is definitely one out to the edge. And that's just in the developed countries. The developing countries certainly probably even a bigger issue there. And then at the colo, certainly for us, the disk I/O issue I think is going to hit us here coming up shortly.
I guess whack-a-mole is a good description of that problem, right?
Yeah.
Well, in terms of computing and storage, I think scaling up, we should think small. The real innovation, I believe, is going to come from nanotechnology or DNA, things at the DNA level. The way we're developing right now with the computing power and the storage, we're going to hit a physical limit at some point. So instead of keep going the way we're going, although we can probably still push it very far, but I believe the new direction is going to be actually thinking small, things that don't even require cooling. And that's my take.
Excellent. Thanks a lot. Okay, so I guess we've got the whack-a-mole or squeezing the balloon problem. We got bandwidth. I'm going to put you guys on the spot, though. And I think if we go back, 15 years, very few people in this room would have predicted we'd be living in a data center-focused environment. And at least I wouldn't have. I can tell you that. I'm asking you to look now forward 15 years from here. What is going to just shock us? Like, who would have ever thought we would be doing this today? And let's confine it to the data center world for that. Put you on the hot seat first,
Sure. Well, I think most of the interesting things these days are a combination of something small like this and a data center. So you think of an iPod and iTunes. You think of my sort of Droid 4 and Google's data centers. And so they're inherently 99% of the processing is happening in the cloud, but it's delivered in a certain way. So the thing I'm excited about is and back when I was at Inktomi, we started thinking about this was I have a device like this. Maybe it's Google Glass. Maybe it's something else. It's something that's on me with a human to machine interface. And if I can apply infinite memory, infinite power, infinite sort of storage to sort of enhance the way that I walk through life. Maybe I just turn on my phone, it listens to everything we're saying, and as I glance down, it's got exactly the thing that I need to know next. It's got all the context of everyone who's here. It's got all of the predictive analytics to really make me more effective as a CEO or as a human or as a father or whatever. So I think it's it's really that next level of how do you think bigger when you have essentially infinite data, infinite processing power, and come up with some business models to fund it a little bit. But you look at the amount of power that I consume when I do a Google search, computing power that is, it's amazing. It's a huge, huge supercomputer that's looking through tons of data. If I applied that to literally every word I took, every step I took, every change in the context of where my friends are and what the news is and so forth, and net that out to the one thing I need to feed into my sort of my moment, I think it's exciting.
Well, it's exciting. I was thinking that when you think about the GPS in your car, the fact that somebody's telling you to take a left at the next intersection, the infrastructure behind that voice message is phenomenal. But fundamentally, that was funded years ago by the government. I mean, the basic high-level infrastructure, the satellites, the GPS system, and you wonder whether, and we're the beneficiaries of that, because that's become accepted to release that, commercialize that kind of technology. I'm not sure that we'll be in that position 15 years from now, frankly. I don't know that the economics of our society are going to enable that kind of basic research to convert to products like that. So I'm not sure it's going to be, I think it's absolutely true that the world is going to become more like us in terms of the access to the kinds of devices we now have. But the big step functions where you really change your life, I'm not positive that it's going to be so different. But then it's hard to predict the future.
Yeah, I mean, I tend to subscribe to Kevin's view of the world. I mean, I'm not, so this is not an advertisement for Google, but we have this thing called Google Now, and I was beta testing it, and I went to my other alma mater, I don't know, 6-9 months ago, and in Indiana, and I landed at the Indianapolis airport, and my phone, because all of my trip itinerary, you know, where I was staying, it was all in Google Calendar, and you know, it basically brought up automatically directions to Purdue, my reservation for my hotel. It gave me directions. It gave me my the radio stations that I want to listen to, Rock and Alternative in Indiana. I didn't have to look for them. It brought up the score of the ball games that I was watching. You know, and it was the weather in Indiana and yada 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 yada. And I have to admit, it was cool, but it was really simplistic. But I think having this massive amount of predictive information, you know, with augmented reality, and whether it's Google Glass or wearable computing, something like that, you know, I think that you're starting to see glimpses of that. And you know, I think that it has massive implications on productivity and the way we're going to interact with the world. And there are certain societal issues, there are certainly privacy issues that we're going to have to deal with. But I think it's really, really compelling, and it's really interesting, because I think it has the potential of really unlocking a lot of human potential, and it's going to be fun to see where it all goes.
Yeah, one of the things I'm kind of really interested for in 15 years, and it's a little bit hard to predict, but I think where we might see a big change is innovation. If you look at the people who are innovating now and go back to their childhood, these are probably people that were tinkering with computers, but they were, you know, 1 in 20 or 1 in 30 kids doing it, and those are the ones doing all the innovation today. If you look at the kids today, you look at, you know, I have friends, they have 2-year-olds, and they pick up an iPad, unlock it, flip through their apps, pick the movie they want to watch, get bored, go back, play a game, and they're 2, right? They can barely complete a whole sentence. That generation, 15 years from now, are going to be the ones innovating. And it's going to be really interesting, I think, to see when the whole generation is comfortable with technology, and then they're in the steering, right, to drive the ship. So I think innovation is going to be a big thing that we see in the cloud. And I think, or maybe not necessarily cloud, just in general. And it's hard to predict what that's going to be, but I think it's going to be really interesting to see this generation grow up this close to technology. And the other thing is this generation is not used to, you know, MS-DOS and keyboards and, right? The 2-year-olds, it's all touchscreen. I wouldn't be surprised if 15 years from now, they don't know what a keyboard is or what a mouse. It just doesn't make sense to sit down in front of a terminal doing something like that. The data is getting more mobile, and I think it doesn't necessarily have to be more complex. I mean, you don't necessarily want more information, but it's easy, right? Whether it's on your phone or it's on the little glasses thing, I think it'll probably get distributed more and more, and the need to sit down on a central computer and do all your work is going to diminish. We've already seen that over time, right? You don't have to sit down and do your email or check the weather anymore. You have the GPS in your car. You don't need a map, or you don't need to check, you know, that kind of thing. So I think those are the two things. The innovation as this generation grows, and they've lived in this environment where it's all touch screens, and then the whole piece of it kind of decentralizing a little bit, and the need for the regular computer to go away.
Well, I think 15 years from now, we will be probably carrying a data center in our pocket. And between AI, between quantum computing, between nanotechnology and some DNA, storing data on DNA, I believe that we'll be living in an augmented reality with everything that we have in our pocket. And everywhere we go, things will be communicated transparently and in a really pervasive way. Thank you.
Excellent. Okay, well, you know exactly what to do now and where the future's going. So if anyone didn't quite get that, I'd like to open this up for questions. Yes.
What happens when we have a big solar flare? Honestly.
Yeah, the question is what happens when we have a big solar flare?
A very quick anecdote. Travelers Insurance had all their data on big tapes, and they built a wonderful new storage facility, huge storage facility, and all the data on tapes. And the fire departments, we have to make sure that this room is fire safe, and they walked through with the walkie-talkies and showed all this to the data. And all of a sudden, they ran the tape and they had the name but not the address. Or the first half of the name but not the phone. Now, what happens when we have these solar panels?
In that case, I think we have bigger problems than our data centers, to be honest. Yeah, the data centers are fairly resilient. I mean, we see, in a Google data center, we see quantum or cosmic ray events occasionally, or we think they're cosmic ray events, a bit flip, a spontaneous bit flip. But again, I think most data centers are built today with a fair to a large amount of resiliency, replication of the data. In my opinion, and I'm certainly not an expert on solar. I've done a fair amount of work in EMP, electromagnetic pulses, in a prior life when I worked with the DoD. That's actually a much bigger concern. But solar events are going to happen, and but again, I think our data centers are built with a fair amount of resiliency, given the amount of solar radiation flux that you have to see spontaneous and catastrophic bit flips. Statistically, that would be a large data or a solar flare that would have other detrimental impacts on life on the planet. So I don't think it's something that we lose a lot of sleep about right now.
No, you don't.
I'm a firm believer in statistics.
Great. Do you have some other questions? Yes.
It's kind of curious. You decided to rethink sorry. So you went through and you saw all this ducting, and you said, we've got to rethink how to get rid of the heat. And I'm thinking, the old IBM 360s, water-cooled. Oh, we improved it now. We can just use air. Oh, we improved it now. We can just use water. How many times do we go through this cycle?
We're going to do it again. But this will be the last time. But the truth is, actually, water is a problem. And one reason they went away from water is because leaks cause damage to the electronics. The concept of using other materials, refrigerants, or in our case, dielectric fluids, has been around forever. There's a firm called Isotope has an interesting video where they actually take an iPhone, they put in their version of the dielectric fluid, and they call it, and it answers. It's completely submerged in this stuff. And it's kind of a fun thing to watch, but the reality is that in the early auto industry, all the engines were air-cooled. But as soon as one changed, they all changed, except for Porsche, right, and Volkswagen, because it was just the better way to do it. It was the right way to do it. They get much more value, much more power out of the same engine. So it's going to move in that direction. There's just too many advantages.
Yeah.
A short model, read that. Let's go back 15 years. NCAR was the absolute progenitor of all of this. The only 96 terabyte memory in the world, and the central processor was the largest Cray. And if you remember, the central processor was floating in a tank of kidney dialysis fluid that was pumped through it. Just
That's
like,
right.
I just
That's
wondered
right.
if you remembered that. Question over here, please, Lindsay. Can you give us some idea about the scaling of latency relative to that brown descending curve on your I/O?
Like network latency or disk I/O latency? For disk? Yeah. So there's I guess there are two. I guess there's different layers of latency, and not to make the answer too long-winded. And I'll talk about the disk one quick. The one that is pretty much impossible to overcome is just propagation delay latency, just waiting for light to travel, and it becomes a pretty big issue pretty quickly. I mean, we have a decent amount of propagation delay just crossing the U.S. from west to east, and certainly if you try to bounce it off a satellite. And there's not much you can do with that. You know, often I make sure that people understand when we're talking about bandwidth that we're designing something for it, that bandwidth just isn't throughput. In my book, bandwidth is throughput and latency, and you can have a high throughput bandwidth with low latency, which is better than high throughput and high latency. So I think those are the two components, and latency is really hard to kind of fix. But you can overcome latency with parallelism, right? If you can do more things at once, you can overcome that with parallelism. So that's kind of the answer there. Now on hard drives, though, latency for, I guess there's kind of two questions. And if it's small data and you need low latency, stuff like SSD technology is going to be, I think, pretty good, or RAM if you can get stuff in the RAM. But when you have big data and want low latency, I think you got to get to that sequential I/O. That's the best trick that I have up my sleeve right now, and that's basically taking out the waiting for that disk to rotate to the perfect position and the head to swing to the right place. You got to get the head down and the disk spinning and just start reading, and that's going to get your latency as low as that we can possibly do it with the hard drives today. I think if that's not enough, then we might need a little bit of a breakthrough in technology on storage.
The pragmatic way it's happening today is with a blend of caching, and so you want a little bit of that turbocharge, and especially if you have a non-random access pattern, but it's something that's a cache-friendly pattern. You can actually get some pretty decent hit rates and serve the hot data out of the hot disk, and have the cold data covering the long tail. And in aggregate, you can then manage the IOP capacity and manage the application response times.
Ultimately, that comes down to fragmentation to efficiency and Jim's predictions about the increase of all of this. There's a crossover on those two things that you're talking about. And I'm curious to know where that's going to occur in terms of usability.
Yeah, I think there's going to be a point where it's going to be really hard if we don't fix, if we don't figure out a technology way to get around that current decrease in IOPS. It's going to be very difficult to actually use the space if they continue to increase this way. I don't know if it's physically possible to keep increasing the disk capacity the way it's been. When I was putting this slide deck together, I saw Western Digital leaked the 5 terabytes that they're working on. So that's probably at least coming, but I don't know if that's going to keep coming or not. But if we keep getting more and more space and we're not getting more IOPS, I think we are going to run into a problem because we're already pretty squeezed in that area.
There's some advances on the flash side coming. You're seeing 1.2, 1.6 terabyte flash drives now. And the cost will be up, but it'll come down pretty quick. So we're starting to see densities that are approaching the same order of magnitude, at least, as spinning rust. And so that's something that you can sort of if you've got big fast data, you can just pay up a little bit more. But I think you have to look at the optimization of that, and then smart infrastructure needs to help with that.
Can I ask one question of Kevin, Jim, Lindsay, and Vincent? Do any of you employ a quantum electrodynamicist in your company, and if so, how many?
So question is quantum electrodynamicist. Do we employ one? Not with that job title. We have plenty of people with physics backgrounds. But yeah, I'm actually not sure.
No.
All right, question in the back?
I have a question. Actually, how do you keep up with the content from 15 years ago? The content size is getting big. What's your plan to keep up with the content?
So how, I think you were asking how are we planning on securing the content?
Well, actually, keep up with the content size because obviously content drives a lot of the network devices.
Sorry.
And actually, the second part of the question is how do you secure that? Because you are doing HTTPS and almost a lot of stuff.
Yeah, I mean, relative to keeping up with the size, we're deploying massive amounts of bandwidth at the edge. So one, so how are we basically keeping up with the content? Yeah, I mean, I saw the statistic, it's public. In the last 2 years, we've uploaded, you guys, have uploaded more content than the 3 primetime networks have produced in their entire existence. So, so one, we don't want to put it all in our data centers. I mean, it ultimately resides in our data centers, but we don't want to put it on our wide area network and our backbone network. We actually want to offload it to the edge and do it in a very, statistically relevant and managed way. But we're just deploying massive amounts of bandwidth. And I mean, that's the only way to do it. And
Have you thought about actually keeping the content on the client devices, on the user devices, and keeping the recipe in the cloud, so that way you don't have to store so much, and of course you have to backup.
yeah, I mean, so the question is, do we consider keeping it on user devices? Mm-hmm. That's right. Yeah. Yeah. I mean, again, it comes down to access. So most people want their content in, 150 milliseconds. So the ability to be able to get it off of a remote device and then get it to a point of consumption would, and we talk speed and latency all the time. I don't think that that's an architecturally feasible way for a latency sensitive piece of content like a video. How we're securing things, that's something, quite frankly, that I don't want to talk about because it's just not secure. The building, I have access to just about every building and door in Google, and the top floor of my building is the security building, and I don't even have access to it because that's where we, this is something that Sergey runs himself. He's very, very, personally attached, as you can imagine, to security. But we're doing some interesting things. Unfortunately, I can't talk about any of them. But I mean, I certainly resonate with a lot of what Benson said. It's not only technology; it's other things.
Certainly, of late, these smartphones that we all walk around with have impinged on the data center just with the amount of stuff going back and forth. Do any of you see any new user devices, whatever they may be, that's even going to jump to the next level in what you have to answer to the user device that you have to support? I think the parallelization of
So the data center is parallelizing to keep up with it, and I think on the other side you're going to see it's not that one device that's going to kick out sort of a this unbelievable new amount of data. It's the number of them. So everything having an IP address, everything having telemetry, everything communicating, everything updating itself, everything coordinating. I think that scale out of sources that's happening right now with just these things. You've seen the tremendous impact it's had and how hard these guys are having to run, and I think that's the bigger source is the number as opposed to the size of an individual one.
Yeah, there's an interesting exercise that somebody gave us, Larry Page gave us the other day. Go home and count the number of displays that you've got in your house and include your cars and garage. And I thought, I went through and did a mental checklist, and we have like 60 different displays in our house, including, and I'm not talking displays, TV displays and computer displays, but displays on our security system, displays on our HVAC system, displays on our water, reverse ionization system,
or osmosis system. All that's going to be enabled with sensors, and it's likely that I think every light socket will have ultimately an IP address on it. So every plug will have an IP address. So imagine, the Internet of Things, when all of that is consuming information and producing information, and that's almost hard to believe. And AT&T did a great study on where the phone will be in 15 years, and it is a data center in your pocket. We do voice recognition today using neural networks, and today those neural networks reside in a data center, but in a relatively short period of time, those neural networks will actually reside in a chip on your phone, and you'll do native voice recognition on your phone or whatever other device you're carrying. And that's, again, all that information is going to be going back and forth between the cloud.
See any kind of paradigm shift in terms of computer architectures in order to handle these kind of security problems?
Well, one comment I'll make is about cost, and that's I had some friends that were working on how do you take all the technology that's hot here and cost reduce it down to where it's cost effective to hand out in Africa. Right, or in rural India, et cetera. And so I think that the evolutionary sort of progression of technology and costs, that research is intense. I mean, you look at all the Moore's law, all the stuff that is intense, and it's happening here in the Valley and in other industrialized nations. And then the question is, how do you right-size that and make that available, and then have business models to take that technology to those new places and help those people unlock the value of that technology and make their lives better. So I think it's really, there's some clever work that you can do to take the things, but I don't think that you're going to invent a new kind of chip and have it be, here's my third world chip. I think it's probably going to be on the same Moore's law curve, and maybe you're just back a little bit, or you're using more of a commodity curve, or you're changing some power assumptions. That's just my perspective, is that you want to be on the volume curve. And then the question is, how can you throw things off of that? And the good news is you only have to go back a couple of years for it to be basically free and very powerful.
I'm going to combine John's question and your question together. I believe in Africa, for example, in China, in India, mobile phone is the #1 computing device everyone is carrying. And I believe mobile phone is going to replace everything you have in your pocket right now. Your key, your money, when you go to your car, your garage opener, it's going to be a remote control when you go home. And in Africa, it's going to be essentially a mobile device for everything that you would do, that we are doing right now. And the only thing they have right now is a mobile system, is a cell system. And just 3G, 4G, that's all they're developing. So I believe mobile phone for them is going to be the future. And it's also for us, it's going to replace a lot of devices we're carrying right now.
Yeah, certainly I'll second that. I do some work for Vodafone, and we're, I think, the second largest carrier in Africa, one of our territories. And the way the mobile phone has changed the life of people in Kenya, one of our more advanced markets, is absolutely unbelievable. And if you want to see mobile payments actually work, go to Kenya. M-Pesa, one of our companies, is got to be the payment company in all of Kenya and Eastern Africa. And it makes it kind of sad when you come back here to the Bay Area and you whipping out pieces of plastic to pay, and when you're in Kenya, you're just kind of using your phone. But, oh well. I guess it teaches you a little bit about lock-in. So, anyway, I think, well, one more question? And sure.
So, the question I have is, where's the human element in this? I mean, the car is a 100-year-old technology, but not everybody has the car. Jeans is a commodity, but not everybody has jeans. So, at some point of time, you're going to level out the economics beyond which this certain part of the population will not be able to consume. So So I'm trying to think, you talked about the bottlenecks to growth and where does it, where do you peak out? I don't know if you think about that, about, you talk about the volume curve and the cost curve. Some point of time, I guess it's going to flatten out, and it's not going to fall because that happened in every industry, in every technology industry. So is that, does that law hold, or do you think we'll break that law in IT?
So a couple of the earlier comments about access, yeah. So I really liked the comments about connectivity and bandwidth, because the interesting part of this is delivering a car or delivering genes or delivering protons is kind of expensive. Delivering electrons is cheaper. And so if you think about, once you get access on something, even if there's only one of these in your village, right? You can actually then leverage the whole sort of tremendous billions of dollars of investment to bring back something. And there's business models that have to go along with that, right? But the incremental the incremental cost of delivering those services is pretty low. The cost of doing a search has been driven pretty low. Back in the day, we used to think of it, I think it cost us a quarter cent or something, and we had to make that up in advertising, and it's probably dropped by 1,000 in that 10 or 15 years. So I think of it as that once you get the access, once you have the pipe and a device to see it, delivering that information and those services, et cetera, a lot of the bottlenecks have been removed versus some of those other markets.
I also think the high technology is going to make everything a lot more affordable over time, and from the last 200 years, anything that we use, the cost has been really relatively going down. So I really think going forward, most technology is going to be more affordable than we think. So I'm not that worried about that.
Great. Well, why don't we call it a wrap at that? I'd like to thank our panelists and Barracuda Networks for hosting us here. And I'll hand this off to the MIT guy who's running the show.
Thank you, David.